Okay, so in this video we'll finally get to Bell's experiment. Okay, so let me review what we are trying to do in Bell's experiment. Remember that in 1964 Bell devised this remarkable experiment which had one of two outcomes. If outcome 1 is true, then nature is inconsistent with quantum mechanics and in fact can be explained by some local hidden variable theory. But if outcome 2 is true, then nature is inconsistent with any local hidden variable theory. It rules out every local hidden variable theory, and in fact nature is consistent with quantum mechanics. And so Einstein's dream of finding this more complete picture for nature, more complete theory, is doomed. Okay, so, and remember this was the abstract setup that we had. Our apparatus was divided into two pieces which were at distant ends of the lab, so that during the course of the experiment light did not have enough time to travel from one to the other. And then we gave to each of these, so each of these pieces of the apparatus we called boxes, and we gave each one, we input a bit, 0 or 1, and each of these spit out or output a bit. And what we wanted was, if both of the input bits are 1, then we want the output bits from the boxes to be different. But in all the other three cases, we want the outputs to be the same. We also showed in the first video that if the boxes are described by local hidden variables, then they cannot succeed with probability greater than 3/4 in this task. We also claimed that Bell showed that there's a way to use in quantum mechanics using entanglement to actually succeed at this task with probability as high as 0.85. So in this video we are going to see how exactly this is achieved quantumly. Okay, so the way it's achieved is by using entanglement. So the two boxes, each of the two boxes is going to contain a qubit, and these two qubits are going to be entangled with each other in this Bell state, 0, 0 plus 1, 1. Now, when the input is given, what we are going to do is we are going to measure the first qubit in one or another basis. So we are going to measure it in some basis which we'll pick. Okay, so we'll measure it in some particular basis, u perp, which depends upon which basis depends upon whether the input was 0 or 1. Similarly, we are going to measure the second qubit in the second box in some basis v perp, depending again on whether the input y is 0 or 1. Which basis we choose depends upon the input. And then if the outcome of the first measurement is u, the box will output 0, and if it's u perp, it will output 1. And similarly, if the outcome of the second measurement is v, the second box will output 0, and otherwise it will output 1. Now, in the last video, we talked about what's the chance that the two outputs match. And we said the chance of that is exactly given by this. So you look at the angle between u and v, and if that angle is theta, the chance that you have matching outputs, that you output 0 in both cases or 1 in both cases, is exactly, so the probability of matching outputs is exactly cosine squared theta. Okay, so what we want to do is we want to set things up cleverly so that in the three cases where we want the outputs to match, cosine squared theta is close to 1. And in the cases that the two outputs are supposed to not match, they are supposed to be different, we want to make sure that cosine squared theta is almost 0. Right? Or sine squared theta is close to 1. Okay, so how do we achieve this? Well, so we have to pick these angles carefully. And in fact, once you think about it a little bit, there's sort of a unique way of picking these angles to maximize these probabilities, the sum of these probabilities, and that's done like this. So let me color code it because I have to use several possibilities. So okay, so let's draw the axes, the measurement bases for the first box first. So in the case that x equal to 0, let's say that we'll do the measurement in the u0 perp basis, which is just the standard basis. And in the case x equal to 1, we'll just rotate this basis by 45 degrees or pi by 4. And let's call this basis u1 and u1 perp. Okay, so now what about the second box? How do we do the measurement? So if y equal to 1, we do the measurement at an angle of pi by 8. So let me draw these dotted lines for the coordinate axes, and then we have an angle of pi by 8 and let's call this v0 perp. On the other hand, if y equal to 1, then we do a measurement at minus pi by 8, right? So sorry, at minus pi by 8, and that's our basis, v1 perp. Okay, so now what do we want from all this? Well, what we want is, in the three cases, we want the angle between the first basis and the second basis to be small so that cosine squared theta is close to 1. And in the last case, where x equal to 1 and y equal to 1, we want the angle to be close to pi by 2 so that cosine squared theta is close to 0. So we get different results in this fourth case. So let's just list out the cases and see how well we do. Well, we can look at x equal to, well, let's look at the case where x, y equal to, and what's the probability of match? Okay, so if x equal to 0, y equal to 0, well then we are measuring in the black bases on both sides, and the angle between them is exactly pi by 8. So the probability of match is cosine squared pi by 8. If x equal to 0, y equal to 1, then we are measuring black here and blue there, but the angle between these is also pi by 8. So the probability of match is cosine squared pi by 8. What if x equal to 1, y equal to 0? Then we have blue here and black here. But look, the angle is still pi by 8. So the probability of match is cosine squared pi by 8. Okay, that's a very nice choice of bases, because we don't have to, we just have this one number to calculate. What about the fourth case? Well, now we have x equal to 1 and y equal to 1. In this case, we are measuring in the blue basis. So the angle between them is pi by 4 plus pi by 8. So it's 3 pi by 8. So the chance of match is cosine squared 3 pi by 8, which is the same as sine squared pi over 2 minus 3 pi by 8. This is the same as sine squared, well, pi over 2 minus 3 pi by 8 is also pi over 8. But in this case, we succeed not when they match, but when they don't match. So in this case, what's the probability of not match? Well, the probability of not match in this case is 1 minus sine squared pi by 8, which is cosine squared pi by 8. So this was a very clever choice of bases, because in each of these 4 cases we succeed with probability exactly cosine squared pi by 8. So the total success probability of this particular strategy, this way of carrying out the experiment, so probability of success is exactly cosine squared pi by 8, which if you work out is approximately 0.85. And this is the content of Bell's theorem. Right? Okay, now let me just say one more thing which might make things a little bit clearer, which is, what did we do here? Well, what we did here was, it's as though we put 4 numbers on the number line. So we put for x we put so this was x0 if x equal to 0, and sorry, let me write this in blue, if this was x equal to 1, and then we put a point down for y equal to 0, and then we put down a point for y equal to 1, and we let the distances between each of these, distances be pi over 8. So think of these as the angles that we had. So these were pi over 8. And now what we are saying is there are 4 cases. Either x equal to y equal to 0, the distance is pi over 8, or x is 0, y equal to 1, pi over 8, or y is 0, x is 1, pi over 8, or x is 1, y is 1, 3 pi over 8. Okay, so this is all we did in setting up those angles. Okay, for some of you this might help make things clearer. If it doesn't, just ignore this. So what did we actually see in all this? Well, to recap, John Bell devised this remarkable experiment which has one of 2 outcomes. Either you do this experiment, you set it up exactly the way quantum mechanics predicts. If the success probability ends up being less than or equal to 3/4, then you have to conclude that nature is inconsistent with quantum mechanics, but it's consistent with some local hidden variable theory. Or you do the experiment and the success probability is strictly greater than 3/4 to within your error parameters, and then you have to conclude that nature is inconsistent with any local hidden variable theory, although it might be consistent with quantum mechanics. The Bell experiment has been performed numerous times. The results have always been consistent with quantum mechanics. There are still a few skeptics who say, well, there are error bars, and if you were to assume, because the detectors are not perfectly efficient, you don't have sources of single photons that are perfectly reliable, and if you assume that all these factors conspire against you in the worst possible way, then it's still possible that quantum mechanics might be incorrect, that it might still be consistent with some sort of other theory. But although dealing with these kinds of loopholes is an interesting question, at this point one would have to say that for all practical purposes, these loopholes are so contrived that we may as well believe that local hidden variable theories have now been ruled out by experiment. There's one last word, which is Einstein spent the last 20 years of his life trying to show that there's a local hidden variable theory that is consistent with everything we know in quantum mechanics, which is consistent with everything we know about nature. It wasn't until about 10 years after his passing that John Bell came up with this experiment. But the remarkable thing to realize is that already in this fourth lecture, in the second week of your, for many of you, first encounter with quantum mechanics, you can already understand something which is simple enough, and yet it is something that eluded Einstein himself, and which, if he had understood, would have saved him 20 years of work. Isn't that a remarkable thing to think about?